Okay, so this is part 2 of our introduction to TensorFlow and keras coding. In part 1, we did a classification neural network that classified these 28 by 28 images into those 1 of 10 classes. And so here we're going to start in part 2. We're going to start with a regression MLP, which is a multi-layer perceptron, and we'll talk about a perceptron as one single neuron. So for here, it's a multi-layer perceptron, which is equivalent to saying just a regular fully connected neural network, or sometimes we call them a vanilla neural network. It's pretty straightforward. Just to draw a picture of what we're talking about here, what you have is your inputs, and then you have some layer. It's going to be your hidden layer, and every input connects to every node in that first layer. Should be a familiar picture. Diagram something like this, and then each node from this layer connects to that layer, and now maybe for the making this pretty simple diagram, that layer is your output. So this would be your hidden layer, and everything from one layer connects to every item in the next layer. Okay, so we're going to use this to do a regression on a California data set. And so let's jump over to here. We can look at the California housing data set in sklearn. It has 8 predictor variables, which are these here. There's a longitude and a latitude, average number of people per household, population, and the idea is to predict the average value of a house on a block. And the output is here. The target or the output that we're trying to match is number, I believe it's like 1 through 5 or 0.5 through 5, and it's the average value of a house in hundreds of thousands of dollars. So I've got blue just for convenience. I run these plots, so we're just going to scroll through these. So we import the housing data set, test print split, and a standard scale, which we can use to scale all of our data to a 0 to 1 range, or a mean of 0, standard deviation of 1. Okay, so here's where we create the data set or read it in. Here's where we're going to create our test train split. And we're going to split our training data into a train section and a validation section. Remember, when we're building neural networks, we train on the training part, we validate that training process on the validation part, and we have a separate part, which we typically call the test part, which we hold that out. Sometimes it's called a holdout data set. We don't touch it to the very end. Okay, so we set some random number seeds. Now here's our multi-layer perceptron, which is really just a simple, fully connected neural network. We're going to use ReLU activations. We're going to have 30 neurons, and then we're going to have a final output, which just has one variable because we're predicting a single value output, which is the average price of the house. And then we go to compile this. This is the sequential neural network model. So we're going to build when we compile it, we're going to make our loss function. It's going to be mean squared error. That's how we measure how good a regression is doing. And we're going to use stochastic gradient descent. And our learning rate is 10 to the negative. And then as we fit, of course, as usual, we save the results for the fitting process in history. And we're going to fit on our training data for 20 epochs. And then specify validation data here. And then we're going to compute the mean squared error on the test. So it says evaluate, and then here we specify the test data. And then we're going to create a new, just a little tiny data set, which is the first 3 observations from the test data. And we're going to try predicting how that. Okay, so we run this. And this took just 1 second for each epoch, and we did 25 to 20 seconds to run. Now then, and then our mean squared error loss we can plot here on the goes down to about a mean squared error of about 4, a little bit under that. So this is our validation loss, which would be the orange. And that's where we level up. And that's, I don't know, maybe it's good, maybe it's not. It's a 0.4 mean squared error. Remember, we're on a level of about 0.5 to 5. So mean squared error of 0.4 means we're about plus or minus $35,000 in our errors. Is that mean squared error or root mean? Okay, so it's mean squared error. So you take the square root of that, would give us some estimate of plus or minus. So maybe that's a little larger. Okay, so we do a prediction, and here we can look at the prediction on those 3. Now, for the sake of testing this, come down here. This spread was text. Here, let's go find out what the actual values are for the estimation. The prediction was trying to predict these 3 values here. So it was 0.477, and we predicted it as 0.7. It was 0.458, and we predicted 1.7. And this one was 5, and we predicted it as 4.2. May or may not be good depending on what level of accuracy. Okay, so here, not all neural networks are simply sequential. Some have complex topologies. Okay, so what we're going to talk about is something with a more complex topology, so we can see how to build this. And so there's this wide and deep neural network, which the length goes to here, and then here's the paper. And if we look at this paper, what you see on this top part, on the left-hand side, we have a wide model, lots of input, single output. A deep model on the right-hand side has multiple layers, and the wide and deep model has 2 parts to it. On the left-hand side is that part that's more the wide part, and then on the right-hand side is the deep part. So that's what we're going to build. What we're going to do is we're going to build a model that has 7 inputs. Right, I guess maybe it has 8 inputs. And for let's check our page. What we're going to do is, well, first we're going to build a model that's just deep, and we're going to see how that works. So we take our input, and then we have a layer, hidden layer 1, which has 30 neurons. Hidden layer 2 has 30 neurons. Then we're concatenating the input, the hidden layer 2, and then we're putting that result, the result of concat, for one more layer, which is dense and has a single neuron. So let's see what that architecture is. So here's, I'm not going to bother writing 30 neurons, but that's 30 neurons. And then here's 30 more. And this is fully connected through here. And then this is fully connected through here. I'm not going to write 900 lines. And then we have one more layer, which is the output. And each of these connects to the output. So there, and each of those connects to the output. So the output, which is this neuron, has this whole layer connecting to it, and the inputs are also connected to it. So it's a more complex topology, not everything going straight through. We have some values that go straight through, and some that take from the input, and then also, it's just what we normally do in connection. You take the value, you multiply it by some weight, and then you add that, and in here, it sums up over all the inputs. Each of the input is multiplied by OP. So let's go and see how that does. And the idea there is that we want to run some of the weights through a neural network, but maybe the simple model is helpful, and we want to put those two side by side. So we're putting the inputs and the result on those. So let's see how this. We have about 1,000 parameters, so it's not too bad. And just to check, our data set has 20,000 observations. So we trained this model through 20 epochs. And we start running, and we hit this thing where the loss just skyrockets, and it's kind of unexpected. And then we start hitting nans, and so that clearly is an indication that our network is not training. And sometimes you'll get that. Sometimes that'll happen because your weights are too large, or you just run off the, like you picture your loss landscape, and instead of running down and getting a nice minimum inside, you just scooch out of the reasonable area. It could be your learning rate's too large. But what we're going to do here is maybe we have some idea that features 0 to 4 and features 2 to 7 have something different going on. So let's go look at features 0 and 1 and features. See if we can see any reason. So I don't know in particular if there's one particular reason. Often you would do this if you have some features that are one type of variable and other features that are different type of variable. Like you had working on an image, but you also knew the location. So you might send all the pixel values through one neural network, and then the latitude and longitude for location of the picture through some other network. And you want to combine them at the end to give your classification. So set our wide random number of seeds, and here's what we're going to do. This neural network is going to have a wide part and a deep part. So the wide part takes input A. So we're splitting the inputs into input A and input B. Input A is going to consist of 5 values, and input B is going to be 6 values. And they overlap on some of the values that they're going to take in. There's 3 values that they overlap. And then hidden layer 1 takes input B as its input. Hidden layer 2 takes hidden layers 1 output as its input. And then we concatenate those two together. And then we send the value of concatenation to our final dense layer. So let's take a look at what this is doing. So as before, this is what our features look like, and we're taking features zero through 4, and we're doing one thing with those. Those are going to go through, those are going to be input A. And so those aren't going to get put through the layers of the fully connected layers, these 2 layers that we're adding. Input B gets put through those, and input B consists of features 2 through 7. So features. So this one's 7 to 0, 1, 2, 3, 4, 5. And I guess I can't count very well. There's 6 and 7. So 2 through 7, those are going to be in input B. And that's going to go through what we call the deep path. So there's going to be a neural network which has 30 nodes, and 2 through 7 are going to be put through that network. And again, I'm not going to draw lines here, but you get the idea. And then those 30 The outputs of those 30 get sent to another fully connected layer. And then we have our output node, and the output of that, those 30 go to the output node. And input A, which is going to have features 0 through 4, it's going to be 0 through 4, and this one I'll mark in red. They go directly to our output neuron. So in red is the wide path, and in black is the deep path. Deep because it's going through multiple neurons. And notice features 2, 3, and 4 go through both paths. So let's see how this architecture works. We go train it. We go through our training, and we get down to a validation loss here. And this probably should have put an error, like the mean squared error output at the end of it. Maybe we'll just work off the loss. The loss is about a 3.6 compared to layer up top. His loss was about the same. So what we're going to do is we're going to add some auxiliary output for regularization, meaning we're going to send the A and the B, and we're going to send them this concatenation layer, and then the output is going to be the output of that concatenated layer sent through to one neuron, but we're going to get an auxiliary output, which is going to take the hidden layer 2 output and send that through an additional neuron. So let's go back to our architecture. What that is doing is a green path that takes these and sends them to another neuron. And each of these 2 neurons are going to try to independently predict the price, and our loss is going to be the net loss between the 2 of these. And so really, in a sense, what we have is we've built one neural network that works on those features, and then a separate neural network which works on, well, I guess it's the whole thing sending through there. And we're going to try to train both of these in parallel. And so that will motivate the deep layers to give us an accurate prediction of the price, and these other, what's shown in red here, is to like amend or be an auxiliary addition to that price. Although I guess that the output in green is what we're calling the auxiliary output. So we're going to try to train that neural network to approximate the price by itself, and then we're going to concatenate the 2 together. And then we have these, we're going to have 2 different losses because we have 2 outputs, output here and then output auxiliary output. And so we have loss weights on those, and we're going to try 90% of our weight loss is going to be getting this, like our main output, which is this one right here, right? That's our main one. But as we train that one, we want to train it to try to get the neural network to learn well. So we're trying to train it so that approximate the price as well. And this 0.1 is the weight for that approximation. Okay, and this learning rate warning isn't a big deal. I should probably put learning rate here instead of LR. Okay, so let's train this for 20 bucks. And we're getting some more complicated output because we have 2 different types of outputs that we're trying to approximate. And then we got our main output loss down to 0.34, which is a little better than the loss that we were able to get previously. So let's just compare That, and this is on our test data. So our test data loss is 0.3425 compared to, see how carefully we had these two. Here's where we evaluated it on our test data, and we got the mean squared error in the test, which was 0.3, about a 0.36 on the test data. And previously we got NANS there. And in our very first MLP, we got to a 0.349, a 0.349. We made it more complicated and we got slightly worse results, but then we built a more complicated model more accurately with a better architecture, and we improved our mean squared error. Okay, so that's good. That's a good example of how the wide and deep, more complex topology. Topology is just like the arrangement of connections between things, or it's the study of geometry without respect to distance. It's the math field with topology definition. So here's a way to build this and to build a wide and deep model. Yeah. Just to rewrite things that we did above in a class. And so here's how we make a class, and then activation method is going to be ReLU. We're going to use 30 units, and we put these here in case we wanted to call that class, but modify those. And we have a hidden layer, which is a dense layer, another hidden layer, which is another dense layer, output, and then this auxiliary output. And down on the bottom, when we do the call, this is how we explain how the outputs are going to be combined. So input A and B. Input B goes through hidden layer 1, the output of hidden layer 1 gets put through hidden layer 2, and then hidden layer 2 output and input A get combined in our concatenation, which gives us exactly this architecture that's in the middle. We take some of our inputs and we send them through the network, through multiple layers of networks, and then we have separate features that get sent directly to the So, same setup, same weights, and then here we just train it for 10 epochs just for a demonstration. Okay, so suppose we have this model and we want to save it somewhere. Suppose we spend a lot of time testing and trying to optimize. And like, oh, I've got a good model. I want to save that model, and I want to be able to recall it so I can use it over and over again. So here's our model, and then well, okay. So for saving and restoring, we're going to make a demonstration model. It's going to be a simple sequential model or fully connected layers, 30-30. And then we compile it for 10 epochs. And then to save it, all we do is model.save. So save is a method that's built into the model. And all you need to do is give it the file name. And then to load it, you just say model equal, and then Keras model load model, and then you give it the file. So pretty straightforward for saving the loading. Model back in. Also, as your models run, one of the things you might want to do is save just the weights for the model, so you can read those weights in for building a new model. And then here's how you build the weights back in. And okay, so let's talk about using callbacks during training. So here we're going to set up how we keep track of the information that's gathered during training. So here we're going to build a simple sequential model, 30 neurons, and then a single neuron output. And we're going to train this with gradient descent, mean squared error, and the loss. So that's how we compile it. And we just set up for training methods. And then here, what we're doing is we're setting up callbacks, model checkpoint, and so this is setting up a checkpoint so that as we're training, if we hit the best model, we're going to save it. We're going to call it my Keras model.h5. and we're going to only save the best model. So as we're iterating, we get a model that's better than the previous model that we found during the training, meaning it has a lower validation error. Then we're going to send, we're going to save that model. So history, right? So here we're doing our fit for our training process. We have 10 epochs. We give it our training data and our validation data. And under callbacks, we add this checkpoint CV or checkpoint callback. And so we're gonna, and then when we're done, what we want to do is apply this Keras load model, and we're going to roll back, load the best model back to memory. This is really important when you train models. Often, after you train it for a while, they tend to overtrain, and the validation error will go downhill, even though your training error keeps going uphill. And so you're going to extract that validation. You want to extract the model from when the validation error was at its best possible, or whatever metric, right? It could be error, it could be mean squared error, it could be cross entropy, whichever. And a lot of times, neural networks, one of the philosophies is they're over parameterized, meaning they have more learning capacity than you need to do the job you're training for. So that allows you to do training, and it allows us to avoid getting stuck on a local minimum. But that extra training capacity also leads you to wind up overtraining. That's why regularization is such a big deal with neural networks. So as we go through this, we are going to save that best model, and then this mean squared error on the test is going to be 3581. I'm not sure which model that it picked, but we should be able to see the validation loss. A lot of times your validation loss, it'll jump around early on. So it starts small, jumps big, then it's down 0.397, 3766, 379. So it looks like this second to last epoch was where we had our best validation. So that's probably the model gets picked, and it probably has a little better validation. Okay, so we compile this again, and we're going to set this early stopping criteria, and patience equals 10 means when we find a best model, we're only going to continue iterating 10 more iterations. And then when we get to 10, we're going to restore the best weight. This is another way of taking a kind of an early stopping criteria. So we're going to train this for 100 epochs, which would take a long time if we didn't have this early stopping criteria. So let's run this fit. It's got our normal training data, our normal validation data, callbacks, keep our checkpoint, and then we have our early stopping callback, which is has this patience of 10 and restores the best ones. So let's see. So I'm reading down, kind of scanning the validation here on the loss on the validation data set. We hit this 0.3602, and we go for probably about 10 epochs after that. So there's a 13. And okay, we stopped at 29. So maybe we got a better one. 18. Oh yeah, okay. So here's the lowest one. And then we don't beat that for 10 epochs. So we're going to keep that one. And then we load that best model in. And look, we get the lowest mean squared error that we've seen so far for any of these models in this data set. So this is creating a function, and on the end of each epoch, what we're going to do is we're going to print the validation loss over the previous loss. And so that indicates how much drop we've got from one epoch to the next. And then we can add this as a callback, and then in our callbacks, just here we have an example. We just trained for one epoch to show this is the validation mean squared error over the train mean squared error, validation loss over the loss, but our loss is mean squared error. And this log means pull it from the log, not take the log function, right? And so our validation error is 96% of the training error, which you can see here, the validation loss is just a little less than the training loss. And so if that number were big, that would be an indication of overtraining. So it's a good example of, as we're training, if we have something specifically to watch, we can have computed from losses. Okay, so here we're going to take a look at the tensor board. I'm not sure if we actually are going to, let's see, we're going to see it in this. Oh yeah, we will see it. So this is a nice feature in TensorFlow that allows us to look at these processes, so something called tensor. So we're going to output our data in this spot called the root log dir, which will be our function. So a log file is, as you're doing any software and you're saving text to see where it goes, your log file is where you would write that to. So we'll make a function that will get the log directory. We import the time, and we're going to, when we write for a log file, usually want to write, okay, at this time, this is what happened. Excuse me. Okay. So, and we'll see more about the log file. So here we're going to clear our Kara section, reset our random number seeds. We're going to make the same neural network that we've been working with. It's got 2 dense layers, 30 neurons each, and then 1 output neuron. We're going to train our loss functions going to mean squared error and our usual variable. Okay, so now we'll train this 30 epochs, and the tensor board callback, it's going to be, we're going to create that out of the callbacks in tensor board, and we're going to read our log directory into the board. The run log dir. And the callbacks are going to have the checkpoint callback and the tensor board. Okay, so here we do our training, and you notice towards the end of our training, we get some large validation losses compared to our training data. So there's some overtraining that goes on at the end, and so we should be able to see that in the tensor. So we can look at the epoch loss. So the tensor board gives us this interaction with our plots. So here we see this. There's this plot. If we look at the kind of the legend at the bottom, the darker black, which is at the very bottom of this plot. Okay. So this is the value, and this is smooth value. So if we take the curve and we smooth it out, so it's an average, maybe plus or minus 1 step. And this is the training loss and the validation loss, and then we have training loss and validation loss again. So this is the black and the blue from one run, and the red and gold are from another run. And you can see the red is on the training data and the black is on the training data, and they're very smooth, and we have a lower loss in those. On the validation data, they start higher, and then as we train, we bring that down. So we can see this 15 epochs or so is kind of a sweet spot. As we get out past 20, we start to see evidence of overtraining. And we could turn some of these off around if we want. And down here, we can look at the evaluation loss versus iteration. Right? So this is how many observations we found. Versus up here, it's a loss as a function of the epoch. Okay. So this is just how to read our directory and using the function we set earlier. So now we're going to run this and we're going to have a ReLU activation, which are in our sequential model of 30-30. So we set this up as before. And we're running log_2. And so that allowed us to get the second series of iterations. So if you look here, check these. In here we had the pink is when we trained for about 12, and the black is when we trained for a larger number of epochs. So we can get the dates for each of those, and then the time is here, and the pink is when we did the second training. The time on the blue in the black, you can see it's 1947-57, so that's when we did it earlier in the day. Apologize for moving the screen around, trying to zoom in a little bit. Okay, so let's talk about hyperparameters. So we have a number of parameters in here, a number of neurons in a layer, the learning rate, and we're going to do some hyperparameter tuning. So in a sense, what we talked about above is the number of epochs as a sort of parameter that we tune. That's how long we do our training gets one step before we overtrain. We're going to talk about how to tune some of the other parameters. So this is going to say, we're going to build a model, and it looks like it's going to be a sequential model, and it's going to look like the models we built before. We're going to add some number of layers. So in is going to be the number of layers, number of neurons in each layer. So previously it was 30, and that's going to be our default. Our learning rate, these are the default values. Default is 3 to minus 3, and the input shape is going to be 8. So this is going to be something that could take in our housing data set. But we could modify the input shape if we wanted, and run this on something else. And in this case, it's the loss is going to be mean squared error, and the optimizer is going to be optimizer chosen here, which is going to be stochastically the same with the learning rate we did. So maybe build model, we should call this maybe build model regression. Maybe we could also build into this like the ReLU activation, and we could also put that as an input value. Okay, so now we are going to call this this scikit-learn wrapper and Keras, and that's going to take in our model and help us with some optimization. So here's what we do. We give it our training data, our validation data, and our callback is going to be the early stopping with patience equals 10. So we're going to train, and then we're going to stop. Let's just take a look at this. I don't think we've talked about this very much. So it's in Keras. And so what this gives is a scikit-learn classifier API for Keras. So it gives a way to interact with the TensorFlow Keras model using a scikit-learn type of interaction or API or front end. And that's going to help with optimization because we can use some of the optimization methods that are available in scikit. Okay. So we're gonna fit, and we already talked about these inputs. We'll do our early stopping. So we stopped here at 21, probably meant the best model occurred at epoch 11, 3, 4, 3, 2. Yeah, it's like that's the best epoch, and it didn't improve for the next 10 epochs. Then mean squared error test says take this and apply it to the test rating, and we get a mean squared error of 0.35 in the test. That's good. It's not the best that we've seen. We've seen a little better than that. And just to take a look at the prediction on X new, we're getting a 0.68, 177, and a 4.8. And those are reasonable. We saw what those first three true numbers were previously.
Yeah.
Okay, so now what we're going to do is use scikit optimization or stop, which isn't here in here. So I'm going to go have to pause my recording and go figure out how I can fix that. Okay, so what I needed to do is to install scikit optimize. So I took import scop, and nice thing in here is that search Stack Overflow. So I searched and browsed around and found out. Pretty sure I needed to import it, but you can't import pip install scop. You need to do pip install scikit. So let's do that, and it runs. Yeah. We're going to do 100 epochs, but I'm expecting we're going to have some early stopping criteria. And what we're going to do, we're going to do a okay, so we're going to do something. All right, so let's talk about this. So we're going to do a Bayes search. And so the parameter distributions, the number of hidden layers, we're going to try 1, 2, or 3, or 0. The number of hidden layers, the number of neurons, we're going to allow that to vary from 1 to 100. And the learning rate, we're going to allow this to go from 3 to the negative 4th to 3 to the 10 to the negative 2. And then we're going to use cross-validation within each of those. And so what this is doing, so let's take a look at the output, because it's it runs for a while, and it's gonna, wow, this is really bad validation. Click it, I'm gonna find one that doesn't do so terribly. And it's gonna look at the validation error, and it's gonna look at the model that it's run, and it's gonna use Bayesian optimization to try to find the best model. We're going to use our patience of 10 to do our early stopping. And let me just peek at, I like this Bayesian optimization. And the thing is, if we used every value here, so if we wanted, if we took, so we would have 100 different values in the number of neurons, 4 options, the number of hidden layers, and this learning rate, it would be a, looks like there's 2 different learning rates that are being chosen. So it's 100 times 200 times 4, it's 800 different variables if we're going to do like a full grid search on this. And doing 10 epochs on each of those 800 sets of input parameters is too large. So we're going to use Bayesian optimization. And that's what we're using here. And there's a nice graphic explanation of what Bayesian optimization does. And, you know, I recommend playing around with this on your own. But the idea is, suppose we want to estimate this curve. This is, suppose, our loss function, or the reciprocal of our loss function, because we're trying to find a peak here. But in our loss function, we try to find the parameters that minimize loss. So we have a bunch of parameters and we want to find the parameters give you the loss. So we pick some parameters at random and we train our model and check the test error. So that's what this red dot represents. And now we want to modify those. We're not going to search through every possible set of values, but we modify them to find something that gives a trade-off between looking for somewhere with lower loss or more accuracy versus exploring areas and values that we haven't tested yet. So here's kind of the theory behind it. But let's just take a look at this picture. So here's where we have our first observation. We know exactly the value here. The black line represents our expected value for, in this case, it's the purple, which is our function f. We're trying to find the maximum of. So let's just go through maximum in this image. So you know, in our neural network, we're trying to minimize loss, but here we want to maximize the purple. So the red gives us the black is our expected value, and the gray band is our uncertainty. And it's 0 at the place we observed, and it grows if you go further away from there until it's whatever our beginning or prior belief was about that spring. So we're going to find the first spot to take our next search point where we have the highest probability of improvement. And there's a couple of different criteria where you can do highest probability improvement or the greatest expected value in improvement or expected amount of improvement. So we get the blue, we get the red there, and so we've explored this, and you notice the next search point is far away because we haven't explored over there, even though we have the expected value, the f function, we're trying to find the next one is lower out here. We haven't explored it, so it's going to go over there. And then here you can see the gray, the top of the gray is the largest around there, and that's really what it's keen on. And so it explores around that maximum to try to find max, and then explores a way to beat down the uncertainty, and then it comes back to find the best. And so you can see it explores more around the maxima, and it explores some far away, but when it says, oh, I've got a lower value somewhere far away, I'm not going to explore it. Okay. Okay, so I'm going to let this run. I'm going to pause the recording and see you in, to me will be a moment, and you will be just be a second.